let's talk forces. Specifically, let's talk about the difference between intramolecular forces and intermolecular forces. So if you think about the prefix on both of these, intra and inter, this is going to help you understand the difference between them. All right, so our different forces, intramolecular forces. These are going to be bonding forces. This is what's going to actually hold a substance, like a molecule together or an ionic substance together, okay? So these are bonding forces. All right, and these are going to exist within each molecule. All right, and these are going to influence the chemical properties of our substance. Okay, so again, these are those bonding forces. So our ionic bonds, that's an intramolecular force. A covalent bond, that's an intramolecular force. Now, all right, this is going to be between our molecules. So these are non-bonding forces. All right, so they're going to exist between molecules. All right, and so these are going to be things that tether things like, so if I have covalent compounds, I have discrete individual molecules. And so a substance that is made up of covalent bonds, a substance that is made up of discrete individual molecules, has to have some way to keep that substance together, like a sample of water. All right, I've got water in my glass here. Well, water is a liquid, all right? Water is a substance that is made up of discrete individual molecules that are held together by covalent bonds. So it keeps each of those individual water molecules hanging out near each other. And these are those intermolecular forces. And so our intermolecular forces, so they're going to influence our physical properties. So our intramolecular forces influence the chemical properties, whereas our intermolecular forces are going to influence the physical properties of a substance. All right, physical properties of the substance. Okay, so we've got our bonding forces exist within each molecule that influence the chemical properties, and then our non-bonding forces are intermolecular forces between each individual molecule, and that looks at our physical properties. Okay, now when we look at the strength of these forces, all right, okay, so again, our intramolecular forces, these are our bonding forces. Okay, and so when we look at these, we've got different types of bonds, our ionic, our covalent, and our metallic. And so when we look here, there's a lot of energy associated with these, and which makes sense because we want bonds to hold things together tightly. The weaker a bond is, the less stable something is, and the easier it reacts. The stronger a bond is, the more stable it is, and the harder it is to get it to react. And so we want things to be held together with strong enough bonds that the substances stay together. All right, and so our ionic bonds, we've got our cation, anion, electrostatic interactions. Covalent bonds, we're sharing those valence electrons. And metallic bonds, we've got those delocalized electrons that are spread throughout the sample. Okay. Typically speaking, our ionic bonds overall are going to be stronger than our covalent bonds. However, okay, if we take a look here, there's a range. We can go from 400 to 4,000 kilojoules per mole, whereas covalent can go from 150 to 1,100. So can we get a covalent substance where the bond is stronger than an ionic substance? Absolutely. But generally speaking, ionic substances typically tend to have stronger bonds than covalent substances do. All right. And then when we look at our intermolecular forces, all right, remember these are between molecules. Right? And this is how we're going to tether substances to one another. And so my glass of water here, what keeps all of my water molecules close together? An intermolecular force. So if you think about it, let's say you are going to go camping, and like my family, you own a camping trailer. Okay, you have to hitch your camping trailer to the back of your car. Well, if I grab, I don't know, here's something I can grab. If I grab this charging cable for my Apple Watch, is that going to be a very strong tether, or is it going to break pretty easily? Now, what if I grab some sort of steel reinforced cable? Is that going to hold it stronger? So there's different strengths of intermolecular forces. In the end, they can all be broken, all right? We're never going to get anything that can never be broken with an intermolecular force, but different forces have different levels of strength. And so we have a whole bunch of different types of intermolecular forces. All right, we've got our ion dipole, hydrogen bond, dipole, ion-induced dipole, dipole-induced dipole, our dispersion forces. Okay, some of these can occur only when I have two different substances mixed together. Others of these can occur within a sample of an individual substance, like my water. Okay, you know what's holding my water together? Hydrogen bonds. All right. Now, when I look at these different forces, it's important to understand the difference between a polar molecule and a non-polar molecule, because some of these forces can exist in everything, whereas other forces require there to be something that is polar. So in your prep class, you should have learned at least about hydrogen bonds, dipole-dipole forces, and dispersion forces, and you should have learned about polarity. But we're going to go back through and review some of this stuff to make sure that you're up to date on this, because these are really important. This is how we hold these things together. Okay, so let's see here. I'm going to put a red asterisk next to things where I can get them existing between a single substance. So all three of those. My hydrogen bond, I can get hydrogen bonds in a pure substance, or I can get hydrogen bonds in a mixture. Dipole, I can get those in a pure substance. I can also get those in a mixture. Dispersion forces, I can get those in a pure substance. I can also get those in a mixture. Whereas my other forces, my ion dipole, my ion-induced dipole, and my dipole-induced dipole, that requires a mixing of two different substances. You have to have a mixture of two different substances to get those. All right? So several of these, though, do require polarity to be present. So what is polarity again? All right? Well, for polarity, we have to understand what a dipole is. All right? So when I look at a dipole, I'm looking at a difference in our electronegativity here. All right? So a molecule such as hydrogen fluoride, which has a positive and a negative end. Okay, so there's a difference in electronegativity between hydrogen and fluorine. So there's a Lewis structure there. All right, which one's more electronegative, the hydrogen or the fluorine? Hopefully you said fluorine, because fluorine's the most electronegative element on the periodic table. And so I can show a polar arrow here, or I can get this partial positive and this partial negative on there. All right, so because of that difference in electronegativity, I get a dipole. All right. All right, so this dipolar character is often represented by an arrow pointing toward the negative end. just like I did there with the hydrogen fluoride. I can do this for something like water. Okay, so oxygen is more electronegative than hydrogen. So I can show my arrows there. Okay, now our dipole moment, all right, this is a measure of the net molecular polarity. Okay, and so what we're looking at is a measured separation of charge. Okay, now we give this in a unit of W's. Okay, we're not actually going to calculate any of these. I might show you some of them, but we're not going to calculate them. All right, now we can have situations where we, have to start judging the overall character of a molecule. And this is where that geometry that we've learned comes into play. When I look at polarity, I have to judge a couple of different things. I have to judge, one, do I have polar bonds? And two, is my molecule itself polar based on the geometry of it? Now, if I have something where everything is identical around the central atom, then that polarity starts to cancel out. But if I have anything different, if I have a mixture of bonds and lone pairs, or I have different atoms bonded, then we start getting a polar molecule. All right, and so we can look at some of these. So something like this chloromethane, I have 3 hydrogens and a chlorine. And so I'm getting a situation where I get this net direction of polarity that goes up through the center there, up through the chlorine, because chlorine is more electronegative than carbon is. Okay, and so we get a net direction of polarity. Something like ammonia, okay, that's that trigonal pyramidal shape. And so I've got that squat pyramid with a lone pair up here, and so we get this net direction of polarity. Water, you may think there's perfect symmetry there because if you divide it down the middle, I have a lone pair and a hydrogen and a lone pair and a hydrogen, but it's not perfect symmetry when it comes to looking at the electronegativity and all of those dipoles. And so you can see here, we've got the hydrogen to the oxygen to the oxygen, and so that converges, and so I get that net direction of polarity up through the center. All right. In order to have a substance that is not polar, you need something that is completely equivalent. So something like carbon dioxide has no net dipole moment because I've got an oxygen and I've got an oxygen. Well, these two are identical things, right? And so if I'm being pulled this way and I'm being pulled this way by something identical, then that cancels out down the center. The tetrachloromethane, okay, I've got that tetrahedral shape. All right, everything is equivalent around the central atom. And so, yeah, the carbon-chlorine bond is polar, but the molecule overall is nonpolar because of that perfect symmetry there. And so when we judge polarity, we have to take this whole picture into consideration. All right, so hopefully that was a review because I know we go over this in the prep class, but if you needed your memory jogged, there's a review of what we're looking at with polarity. Now, when I look at different phases of matter, when I look at my solid versus my liquid versus my gas, we know a few things about these, right? Because we've studied chemistry for a little bit. We know that our gases are super far apart from each other and they have these low densities, all right? Our liquids are close together. We know that our solids are even closer together. Okay, solids have a definite shape, whereas our liquids and our gases do not. But when I look at those intermolecular forces, so IMF is an abbreviation for intermolecular force. Okay, so when I look at the strength of intermolecular forces, my solids have stronger, Liquids have a moderate intermolecular force strength, and gases have a fairly weak intermolecular force strength. And this makes sense because if my gas particles are super far apart from each other, they're not interacting much with each other, and so those intermolecular forces aren't very strong. But my liquids and my solids are much closer to each other. Okay, liquids have slightly weaker intermolecular forces than solids because liquids, everything is moving around each other, right? But solids, everything's rigid and hard together. So when we think about our different phases of matter, we can also think about the strength of those intermolecular forces. And understanding this helps to understand phase changes, which we'll talk about. Because if I think about the amount of energy it takes to go from a solid to a liquid or a liquid to a gas, if I think about the strength of those intermolecular forces, well, if gases have weak intermolecular forces, but liquids have stronger ones, how hard is it to go between a liquid and a gas? So something to think about. All right, and so we will take a look at a whole bunch of these things as we're looking at this bigger picture.